Okay, from where we left off, going back to the 2.5 lecture, we did each of these. Moving along. Let's define continuity from the left versus continuity from the right. So if we just say continuous, kind of like a limit, we're implying from both sides. But we can define continuity just from a single side, from the left or from the right. F of x is continuous from the left at x equals a if the left-sided limit is equal to the function value. And f of x is continuous from the right at x equals a if the right-sided limit is equal to the function value. So let's take a look. This example will have two parts. This piecewise function would be a good highlight this well. H of x equals x squared when x is less than 1, and the natural log of x when x is greater than or equal to 1. So in part A, is h of x continuous from the left at x equals 1? So we're thinking, okay, continuous from the left, so that's when the left-sided limit has to equal the function value. So we'll look at both of these. Let's start with the left-sided limit. Okay, there's the question. Does the left-sided limit of h of x as x approaches 1 from the left, does that equal h of 1? We're thinking if 1 is in question, then we'll put in, a 1 in for the a's. As we approach 1 from the left, does that equal h of 1? Let's look at the limit first. Well, as we approach 1 from the left, we're going to take the piece that represents values a little bit smaller than 1. So we'll take the x squared, and we can simply plug in, and we get that limit to equal 1. Okay. How about the function value? H of 1, which piece do we need to use there? And we need to use the natural log of x because that is where x can equal 1. And it turns out that the natural log of 1 is equal to 0. So is h of x continuous from the left at x equals 1? No, it's not continuous since those did not equal each other, 1 versus 0. How about same piecewise, but now continuous from the right at x equals 1? The question is the right-sided limit as we approach 1 equal to h of 1? We look at the limit first. Turns out we're approaching 1 from the right side. We need to use the natural log of x. Get the natural log of 1, which equals 0. And that will be the same for h of 1. Well, because h of 1 is where it's equal, that happens to also be on the right side. You get 0 again. And so, yes, this is continuous from the right since they're equal. I can't help it. Let's do a quick graph. I just like graphing these piecewise functions. That's always. Okay, so we got x squared, where x is less than 1. And the natural log of x, where x is greater than or equal to 1. So what's happening? Well, we see that jump. And the key is, where is the equal sign here? So on the left, we have the hole at the top. On the right, that the point is there because we can equal. And so we're not continuous on the left because that left-sided limit did not equal the function value down here at 0. But on the right side, it did. It was going to the point itself there. Okay. Kind of where is this leading us? Well, now that we've discussed one-sided continuity, let's go back to our theme of just regular continuity, two-sided continuity. Here's a theorem, kind of a smaller theorem, just to note. These functions are continuous on their entire domain. This is going to be really, really useful. These 7 functions, polynomial functions, are always continuous on their entire domain. They don't have any jumps or holes or asymptotes. A rational function is continuous on its entire domain. You might think, wait a second, a rational function, we dealt with something like that earlier, and it had a hole and a vertical asymptote. You know, we saw that before. Yes, but those values were not in the domain of that rational function. So there's kind of a nuance here. We're saying these are continuous on their domains. So if there are x values which cause, say, division by 0, then we wouldn't count that x value in the domain in the first place. And what we're really trying to get at is every other value it is continuous at, every value that's in the domain. So that might seem like, you know, we're cheating or something, but you know, hey, that's how it plays out. How about a root function? So any square roots or cube roots, they're always continuous on their domain. Trig functions, same thing. Now that, you know, kind of the same issue gets brought up, like what about tangent? Tangent has vertical asymptotes. Yes, but those are not considered in the domain. Anything that's in the domain, you're good. Inverse trig, same idea. Exponential functions and logarithmic functions, again, always continuous on their domain. Why is this helpful? By itself, it's not really that helpful. We're going to combine that theorem with this next one. If f of x is continuous at x equals a, which we know all of those functions above are always continuous on their domain, okay? If f of x is continuous at x equals a, then the limit as x approaches a for f of g of x is equal to f of, and you see we push the limit inside the limit of g of x as x approaches a. This is actually a really, really big concept, a big theorem. It's going to be incredibly helpful for us. How, you might ask? Let's look at just a quick example of how this is useful and how this will make taking certain limits really fast when maybe they would have been a headache otherwise. What if we wanted to do the limit of cosine 2x squared as x approaches 0? Okay, so we say, all right, well, wouldn't it be great if we could just plug in the 0? And yes, that would be great. And it turns out we can, because we know that cosine is always continuous on its domain. It's a trig function. So we could rewrite this limit as the cosine of the limit as x approaches 0 for 2x squared. Now, to take the limit for 2x squared, all we need to do is plug in. We know we're fine doing that. Well, plugging in here, well, 2 times 0 squared is 0. So we're taking the cosine of 0, and, well, we can simplify that equal to 1 for our final answer. And essentially what happened, because we're allowed to move that cosine, you know, kind of switch places with the limit, we essentially just plugged 0 in for x. It's kind of the takeaway here. Whenever finding a limit for any of those 7 types of functions for a value that is on its domain, all we got to do is plug in. Now, if you were actually doing the work by hand at this point, I would suggest don't even bother showing that middle step where you're pushing the limit inside the cosine. Just plug right in, because you know you're good. So if you were taking the limit as x approaches 0 for 2x squared, boom, plug it in. I'm taking the cosine of 0. That's equal to 1. Got my answer. Fast, simple. Cosine is continuous, you know, on the entire number line, it turns out. So anything, we can just plug it right in and we're done. Okay. The last part of 2.5 is the intermediate value theorem, the IVT, we call it. Intermediate value theorem is pretty cool. Let's take a couple minutes. You know what? Let's stop this video here. So I see the time. We'll pick it up. We'll explain this one and do an example in the next one.